In the deepest, darkest space between galaxies, something incredible is happening. Every cubic centimeter of emptiness seethes with a hidden energy so vast it could power our civilization for billions of years. Here, virtual particles erupt from nothingness, borrow impossible amounts of energy, and then vanish before the universe even notices. This is the story of nothing, and it's the most important and terrifying story in the cosmos. We will journey through laboratory experiments that conjure light from a pure vacuum. We'll discover cosmic voids stretching 300 million light-years across, yet teeming with invisible forces. And we'll explore how the very emptiness around you could suddenly, catastrophically, rewrite the laws of physics faster than the speed of light. If you're ready to question the very fabric of reality, join the Stellify Science community. Subscribe now, and let's journey into the unknown together. Prepare yourselves. We begin. Your coffee cup sits on your desk, apparently empty, but this is a profound illusion. It contains quadrillions of air molecules, a chaotic swarm of nitrogen and oxygen racing around at over 1,500 miles per hour. Most people think empty means nothing exists there, but walk into what seems like an empty room, and you're actually swimming through a turbulent ocean of invisible particles. Each breath you take contains roughly 25 quintillion molecules. These particles, far too small to see, crash into your skin about 10 trillion times per second, creating the constant, gentle pressure of the atmosphere we feel every moment of our lives. When you wave your hand through what you perceive as empty air, you are in fact bulldozing your way through a near incomprehensible number of molecular collisions. Your hand displaces a number of air molecules so large it's written as 1 followed by 23 zeros every single second. Think of these air molecules like microscopic ping-pong balls, ricocheting everywhere at incredible speeds. In your seemingly empty coffee cup, these molecular projectiles zoom around at about 500 meters per second. Faster than a speeding bullet, faster than the speed of sound. They relentlessly slam into the cup's interior walls millions of times per second. Each individual collision is infinitesimal, a whisper of a force you could never feel. But together, these countless impacts create enough collective force to support the weight of the entire column of atmosphere stretching from your desk to the edge of space. The sensation of temperature is nothing more than the average speed of this molecular motion. The molecules in hot coffee are simply bouncing around faster, while the air in a cold room contains the same molecules, just moving more slowly. Even at the coldest temperatures humans have ever created, a fraction of a degree above absolute zero, this molecular motion never completely stops. But this frantic dance of air molecules is just the beginning of what fills this empty space. Light waves from the lamp above you constantly stream through your cup. Radio waves, carrying broadcasts from across the city and signals from galaxies millions of light-years away, pass right through it, completely unimpeded. Cosmic rays, high-energy particles blasted from the hearts of exploding stars, penetrate the ceramic walls and keep going, traversing the room in the blink of an eye. Neutrinos, ghostly particles born in the nuclear furnace of the sun, zip through your cup, your desk, your entire body, and the Earth itself as if none of it were even there, continuing their silent journey through the cosmos. Beyond particles, every point in this space is permeated by invisible fields of force. Your cup sits within Earth's magnetic field, the same ancient force that has guided mariners' compass needles for centuries. Electric fields, generated by the electronic devices on your desk and the wiring in your walls, create complex, invisible patterns throughout the empty air. These fields are not passive. They carry energy and can exert a push or pull on charged particles, even when no tangible matter is present. Even after all this, we have barely scratched the surface of what nothing truly is. Scientists have discovered that even if you could achieve a perfect vacuum, a feat far beyond our current technology, and remove every last air molecule, every photon of light, every stray electromagnetic wave, something extraordinary would still remain. The quantum fields that are the fundamental building blocks of all matter and energy never completely disappear. They continue to fluctuate, to vibrate, even in the deepest, coldest, most perfect emptiness imaginable. Modern physics reveals a startling truth: perfect nothingness cannot exist. The universe abhors a true vacuum more than nature supposedly abhors a regular one. Your simple coffee cup is a profound demonstration of how deeply wrong our everyday intuitions about emptiness really are. What looks empty is, in fact, a stage for a constant, invisible storm of activity. Molecules race around faster than fighter jets. Electromagnetic fields weave intricate patterns through space. Light and radio waves stream through continuously. And even if you could somehow remove all of this, the underlying quantum fields would keep the space from ever being truly empty. The deepest vacuum chambers humans have ever created, marvels of engineering, still contain thousands of particles per cubic centimeter. Perfect emptiness remains beyond our grasp. Yet even if we could create it, something would still be there. But the space inside your coffee cup appears crowded and bustling when compared to the emptiness inside the very atoms that make up solid matter. The gap between the nucleus and the electrons in a single carbon atom is so incomprehensibly vast that it could fit 10,000 virus particles lined up side by side. Atoms are, overwhelmingly, empty space. If you were to enlarge a single hydrogen atom to the size of a modern football stadium, the nucleus, the proton at its core, would be no larger than a single marble sitting at the 50-yard line. The atom's single electron would be a tiny, almost dimensionless speck, orbiting somewhere in the stadium's distant upper seats. Everything else, the entire volume of that colossal structure, would be, to all appearances, completely empty. This staggering emptiness makes up nearly all of the matter around you. Your coffee cup, your desk, your chair, even your own body, consists almost entirely of empty space between subatomic particles. The actual physical stuff that makes up your atoms, the protons, neutrons, and electrons, takes up less than 1/trillionth of their total volume. You are, in a very real sense, a sophisticated cloud of emptiness, given form and substance only by the ceaseless dance of electromagnetic forces. For a time, scientists thought this atomic emptiness was truly empty. Early models of the atom pictured electrons orbiting the nucleus like planets around the sun, with nothing but a perfect, classical vacuum in between. These planetary models seemed to explain how atoms worked, but they missed something crucial, something fundamental about the nature of space itself. Quantum mechanics shattered that simplistic illusion. It revealed that this atomic emptiness seethes with a ferocious, hidden activity. Even at absolute zero, the theoretical temperature where all molecular motion is supposed to cease completely, the electromagnetic field between atomic particles refuses to be still. It keeps vibrating. These irreducible vibrations represent the lowest possible energy state of the universe, a state known as zero-point energy. Every point in space, from the vast gulfs between galaxies to the tiny regions inside atoms, contains this fundamental quantum energy. And the amount of zero-point energy hiding within this emptiness defies all comprehension. Physicists' calculations, grounded in the proven theories of quantum fields, suggest that every cubic centimeter of empty space contains enough latent quantum energy to boil all the water in all of Earth's oceans. A single coffee cup's worth of this quantum vacuum energy could power human civilization for millions of years. The empty space inside your own body contains more raw energy than all the stars in the visible universe combined. This staggering energy arises from the very nature of quantum fields. Unlike in classical physics, where empty space has zero energy by definition, quantum physics requires and demands uncertainty in energy levels. The more precisely you attempt to measure the energy in a given region of space, the more uncertain that measurement inevitably becomes. This fundamental uncertainty translates into constant, unavoidable energy fluctuations, even in a perfect void. A useful analogy is to think of quantum fields as the surface of a stormy ocean that can never become perfectly calm. Even when no large waves are visible, tiny chaotic ripples constantly keep the water moving. Quantum fields behave in a similar fashion, with these zero-point fluctuations happening at every point in space and at every moment in time. Every type of quantum field, the electromagnetic field, the electron field, the quark fields, all contribute their own zero-point motion simultaneously. Since these fields have a theoretically infinite number of oscillation modes, the total calculated energy becomes infinite, a problem that points to one of the deepest challenges in modern physics. These relentless fluctuations give rise to one of the most bizarre and consequential phenomena in all of physics: virtual particles. These are not just theoretical constructs. They are real disturbances in the quantum fields that erupt into existence from nothing and then, almost immediately, disappear back into it. Virtual particles are not science fiction. Their effects are measurable and have been confirmed by decades of experiments. Virtual photons, for example, act as the carriers of the electromagnetic force. The repulsion you would feel between two magnets, or the attraction that holds the atoms in your body together, is mediated by a constant, invisible exchange of these virtual photons. Life itself exists because of these phenomena happening in supposedly empty space. The quantum vacuum operates like the universe's most exotic and accommodating bank. Virtual particles are constantly making massive energy withdrawals from nothingness, but the banking rules are strict. They must pay the loan back so quickly that reality, bound by the laws of energy conservation, never officially notices the missing funds. This quantum lending system is what powers the fundamental forces that construct our world. It's all made possible by Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. The principle states that certain pairs of properties, like energy and time, cannot both be measured with perfect precision simultaneously. This inherent uncertainty creates tiny loopholes in the rigid laws of energy conservation. Virtual particles are the ultimate opportunists, exploiting these loopholes by borrowing huge amounts of energy for incredibly brief periods. The more energy a virtual particle borrows, the shorter the time it is allowed to exist. A virtual electron-positron pair, for instance, can borrow enough energy to equal the mass of an entire planet, but it can only exist for less than 1/septillionth of a second before it must vanish without a trace. These impossible energy loans are happening everywhere, all the time. In the seemingly placid space between your fingers right now, virtual photons, virtual electrons, virtual quarks, and dozens of other types of virtual particles are continuously popping into existence and disappearing. By some estimates, every cubic centimeter of empty space experiences roughly 10 to the 45th power of these virtual particle events every single second. Think of them like lightning that strikes in reverse. Instead of building up charge and releasing it in a dramatic flash, virtual particles release enormous energy instantly, then spend almost no time existing before vanishing. They are like cosmic fireworks that explode before they're even lit. Typically, virtual particles appear in matter-antimatter pairs and almost instantly annihilate each other. An electron and its antimatter counterpart, a positron, might briefly materialize, circle each other once in a fleeting dance, and then crash together, disappearing back into the quantum foam. The total energy borrowed is zero because the electron's properties cancel out the positrons, and overall energy conservation is maintained. But under extreme conditions, this perfect symmetry can be broken. Near the event horizon of a black hole, the gravitational pull is so immense that it can affect this process. One member of a newly formed virtual particle pair might fall past the point of no return, while its partner escapes into space. Robbed of its partner for annihilation, the escaped particle is promoted to the status of a real particle. To pay its quantum debt, it must steal a tiny amount of energy from the black hole itself. This process, predicted by Stephen Hawking and now known as Hawking radiation, means that black holes are not truly black. They glow ever so faintly, and over immense timescales, they can slowly evaporate by losing energy to virtual particles born from the vacuum at their edge. This also leads to the famous black hole information paradox. Quantum mechanics insists that information cannot be destroyed, but Hawking radiation appears to be completely thermal, carrying no information about what fell into the black hole. If a black hole evaporates completely, where does the information go? It's a profound puzzle that pits our two best theories of the universe against each other. Strong electromagnetic fields can also tear virtual pairs apart before they annihilate. Physicists have predicted that electric fields powerful enough could rip virtual electrons away from virtual positrons, creating real particles from a pure vacuum. Such fields would need to be stronger than those found around ordinary atomic nuclei, but they might exist in the extreme environments near neutron stars or during violent cosmic collisions. Laboratory experiments have detected the influence of virtual particles indirectly for decades. The Lamb shift, a tiny but measurable difference in the energy levels of hydrogen atoms caused by the jiggling of virtual particles, was one of the first pieces of evidence that these quantum vacuum fluctuations really occur. But perhaps the most striking and direct proof of the vacuum's latent power is a phenomenon known as the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir was analyzing the nature of virtual particles when he made a bizarre prediction. He proposed that if you take two perfectly parallel metal plates and place them in a perfect vacuum, separated by a gap thinner than a human hair, they will spontaneously be pushed together by a measurable force. He realized that the empty space between the plates would contain fewer types of virtual photons than the space surrounding the plates. This imbalance, he argued, would create a net pressure, a real physical force, pushing the plates inward. To understand why, think of the virtual photons in the vacuum as invisible ocean waves with an infinite variety of different wavelengths. In open space, waves of all sizes can exist freely, pushing on objects from every direction. But between the two closely spaced metal plates, only waves with wavelengths shorter than the gap can physically fit. The longer waves are excluded, like trying to fit a full-sized surfboard through a narrow doorway. This exclusion creates a powerful imbalance. Outside the plates, all possible wavelengths of virtual photons are pushing inward. Inside the gap, only the short wavelengths are pushing the plates apart. The result is a net inward force, squeezing the plates together. Incredibly, space itself becomes a spring that compresses the plates. This force is extraordinarily weak, but it is real and has been precisely measured in laboratories around the world. Two perfectly parallel metal plates separated by just 1 micrometer experience a Casimir force, equivalent to the weight of a single red blood cell, pressing on an area the size of a football field. Scientists have measured this using incredibly sensitive instruments, like microscopic metal spheres suspended by thin fibers, capable of detecting forces as small as 108 newtons, like measuring the gravitational pull of a grain of sand from 20 meters away. Despite being tiny, its confirmation is a landmark achievement. The Casimir effect provides irrefutable proof that empty space has a complex structure and is filled with energy. Virtual particles are not just mathematical abstractions. They are real disturbances in the quantum fields that can exert a tangible push on physical objects. Empty space, it turns out, can have pressure, tension, and mechanical properties just like ordinary matter. This perpetual motion of the quantum vacuum enables even stranger phenomena. If you can manipulate the boundaries of a space, you can manipulate the virtual particles within it. Recently, Finnish physicists used an array of 250 superconducting circuits to generate real photons from apparently empty space. They demonstrated what is known as the dynamic Casimir effect, where moving boundaries can convert virtual photons into real, detectable particles of light. The researchers couldn't physically move mirrors at nearly the speed of light, which would be required, so they ingeniously created an electronic equivalent. They built a system where they could change the optical properties, effectively the speed of light within their device, faster than the virtual photons inside could respond. Think of this like violently shaking a fish net underwater. If you move the net slowly, water simply flows around it smoothly. But if you shake it rapidly and erratically, you create turbulence and generate real, tangible waves. The Finnish experiment shook the quantum vacuum so fast that it agitated the virtual photons, giving some of them enough energy to break free and become real photons. The quantum vacuum, for a moment, literally glowed with this newly created light. The generated photons had exactly the properties that quantum field theory predicted, appearing in entangled pairs, a clear fingerprint of their origin from the vacuum. For the first time, scientists had directly and unambiguously observed the conversion of virtual particles into real ones through purely quantum mechanical processes. They had created light from nothing. This breakthrough probes the very boundary between the virtual and real worlds, and it may one day have practical applications in quantum computing and communication systems. The energy hidden within the quantum vacuum is staggering, a sea of potential just beneath the surface of reality. But even this pales in comparison to what astronomers have discovered lurking in the vast, silent emptiness between the galaxies. When we look at the universe on the largest scales, we see a stunning cosmic web of galaxy filaments and massive clusters where matter has congregated over billions of years. But this web makes up only a fraction of the cosmos. About 80% of the universe's total volume consists of enormous, almost empty cosmic voids. The Boötes void is a famous example, a colossal cosmic desert stretching some 330 million light-years across. This single void contains only about 60 known galaxies in a volume that, based on the cosmic average, should hold 10,000. It is one of the largest and emptiest structures ever discovered. Yet even this seemingly barren region isn't truly empty. It's filled with a host of invisible phenomena that shape the course of cosmic evolution. Incredibly sparse, tenuous threads of dark matter are thought to stretch across these voids, forming an unseen skeleton for the cosmos. The cosmic microwave background radiation, the ancient fossil light from the Big Bang, fills every cubic centimeter of void space with a uniform, cold glow. Vast but incredibly weak magnetic fields, perhaps relics from the early universe, permeate these empty regions. Ghostly neutrinos, high-energy cosmic rays, and the gentle ripples of gravitational waves all stream through these cosmic voids, their journeys almost entirely unobstructed. But dominating all of these is a mysterious, pervasive force that fills every single point in space: dark energy. This unknown component makes up roughly 70% of the total energy density of the universe, and it is responsible for the single most profound discovery in modern cosmology: the fact that the expansion of the universe is accelerating. In dense regions of the cosmos, like our own galaxy cluster, gravity's attractive pull easily overwhelms the effects of dark energy. But out in the vast emptiness of the voids, dark energy reigns supreme. Astronomers discovered dark energy by meticulously studying distant Type Ia supernovae, exploding stars that act as standard candles for measuring cosmic distances. To their astonishment, they found that these distant lighthouses appeared dimmer and therefore farther away than they should have been in a universe whose expansion was slowing down due to gravity. The only explanation was that, for the past 5 billion years, the expansion has been speeding up. Think of dark energy as an invisible, repulsive spring embedded in the very fabric of space itself. The more you stretch the spring by expanding space, the harder it pushes back. As the universe expands, dark energy's repulsive force grows stronger, accelerating the expansion even faster. This creates a runaway process that will shape the ultimate destiny of our cosmos. The nature of dark energy remains one of physics' greatest mysteries. The simplest model, the cosmological constant, treats it as an inherent, unchanging property of empty space itself, an idea Einstein first proposed and then called his biggest blunder. Other ideas, like quintessence, propose a dynamic field that can change over time. Still, other theories attempt to modify gravity itself on cosmic scales. The effects of dark energy only become noticeable across hundreds of millions of light years. Within our local group of galaxies, gravity is still the dominant force. The great Andromeda galaxy remains on a collision course with our Milky Way, and they are destined to merge in about 4 billion years. But on the largest cosmic scales, dark energy's cumulative push is stronger than the gravitational attraction of all the matter in the universe. Its continued dominance ensures that the universe's far future will be one of increasing isolation, cold, dark, and empty, as galaxy clusters become lonely islands separated by ever-growing voids of nothingness. Yet, there are places in the universe where forces even stronger and more concentrated than dark energy can reshape the very structure of empty space. A neutron star is the collapsed core of a massive star, an object packing more mass than our Sun into a sphere only about 12 miles across. Its surface gravity is 600 billion times stronger than Earth's, but its magnetic field represents the most extreme force in the known universe, reaching strengths of 1 trillion Tesla, a power so immense it can literally bend the quantum vacuum. These colossal magnetic fields arise from the collapse of massive stars during supernova explosions. As the star's core contracts, its magnetic field lines are compressed and twisted into incredibly concentrated knots, amplifying their strength by factors of millions. This field is so powerful that it affects the virtual particles in the surrounding vacuum through a phenomenon called vacuum birefringence. The virtual electron-positron pairs that constantly pop into existence are polarized by the magnetic field, which slightly changes how light waves propagate through that region of empty space. This bizarre effect splits a beam of unpolarized light into 2 separate beams, much like how certain crystals can polarize light. The splitting happens in what should be completely empty space, because the virtual particles in the quantum vacuum are forced to act like an optical medium. The strong magnetic field turns the vacuum itself into a type of lens. In a landmark observation, astronomers detected this vacuum birefringence effect around a neutron star using X-ray telescopes. These observations provide direct, tangible evidence that virtual particles are real and that their behavior can be influenced by external forces. The quantum vacuum isn't just a passive mathematical backdrop, it's an active physical medium that can be bent and shaped. In theory, the strongest neutron star magnetic fields, found in a special class of objects called magnetars, might even approach a critical field strength where they could rip virtual particles apart with such force that they become real, creating matter and antimatter directly from pure electromagnetic energy. The intense gravitational field near a black hole's event horizon can tear virtual particle pairs apart, causing one partner to fall into the black hole while the other escapes as real Hawking radiation. This demonstrates how extreme gravity can convert the energy of the quantum vacuum into observable particles. But this is just one example of how space itself actively participates in the creation of new matter and energy. Every single second, the ongoing expansion of the universe creates roughly 10 to the 78th cubic meters of new space. That's more new volume than all the atoms in the observable universe occupy. This space doesn't expand into anything else. New space simply comes into existence everywhere, simultaneously. General relativity, Einstein's theory of gravity, predicts that space itself can be created or destroyed. During a period of cosmic inflation in the universe's first fleeting moments, space expanded at exponential rates that are difficult to even imagine. A region of space smaller than an atomic nucleus grew to be larger than a basketball in less than 10 to the negative 30 seconds. This inflationary epoch generated virtually all the space in our observable universe today. This hyper-expansion was driven by a special scalar field called the inflaton, which created our entire cosmos from a single microscopic quantum bubble. Inflation elegantly solves several profound puzzles about our universe's properties. It explains the horizon problem, why the cosmic microwave background radiation has almost exactly the same temperature in all directions, even from regions of the sky that should never have been in thermal contact. Inflation explains this uniformity by taking a tiny, thermally equilibrated region and expanding it to cosmic scales. Think of it like a photocopying process that takes a tiny, smooth patch and enlarges it to an enormous size. Inflation also solves the flatness problem, explaining why the geometry of our universe appears to be perfectly flat on large scales. Any initial curvature of space, no matter how extreme, would be stretched out and flattened by such an enormous expansion. The colossal energy that powered inflation came from the inflaton field's potential energy. When inflation ended, in a process called reheating, this energy was released and converted into the hot, dense plasma of particles and radiation that filled the early universe in the event we call the Big Bang. The tiny, unavoidable quantum fluctuations in the inflaton field during this inflationary period were also stretched to astronomical sizes. These primordial fluctuations became the seeds for all of the structure we see in the universe today, the galaxies, the clusters, and the great cosmic web. We are, in a very real sense, the physical manifestation of quantum fluctuations in the primordial void. This cosmic origin story leads us to the most profound and potentially terrifying question about the nature of nothing. Is the vacuum state of our universe truly and eternally stable, or is it merely a temporary metastable state, perched precariously on a cosmic ledge, waiting for a nudge that could cause it to collapse into something else entirely? Current physics, based on our best measurements of the universe, suggests that our universe might exist in what is called a false vacuum, like a ball that has come to rest on a small ledge on the side of a hill. Rather than at the very bottom of the valley, our reality appears stable, but a sufficient disturbance could send it rolling down into a deeper, more stable valley, the true vacuum state. The transition would not be gentle. It would release an immense amount of energy and fundamentally alter the constants of nature. It would be a cosmic phase transition. But instead of water freezing into ice, the very rules that govern reality would change. The Higgs field, the quantum field that permeates the universe, giving mass to fundamental particles, is the most likely candidate for this potential instability. Precise measurements of the Higgs boson's mass, along with the mass of the top quark, place our universe uncomfortably close to the theoretical boundary between eternal stability and inevitable, eventual decay. We appear to be balanced on a cosmic knife's edge. If the Higgs field truly exists in a false vacuum, a random quantum tunneling event could, at any moment, anywhere in the universe, Trigger the decay to the true vacuum state. A small, microscopic region of space could randomly fluctuate into this lower energy configuration, creating a bubble of the true vacuum. This bubble of new physics would then expand outward in all directions at nearly the speed of light. You would never see it coming. There could be no warning. The bubble wall would be a shell of pure energy, more powerful than anything in the known universe. Anything that encountered it, planets, stars, galaxies, would be instantly vaporized. But the destruction inside the bubble would be far more fundamental. The very laws of physics would be different. The mass of the electron might change, or electrons might not be able to exist at all. The strength of the strong nuclear force could shift, causing all atomic nuclei to disintegrate. Chemistry as we know it would become impossible. Stars, planets, and any form of life would be erased from existence, replaced by an entirely new and alien reality governed by completely new and alien rules. Some calculations from the 1980s by physicists Sidney Coleman and Frank DeLucia suggested that such false vacuum bubbles would immediately collapse under their own immense gravity, forming a black hole. In this scenario, not even the new physics inside the bubble could survive. The good news is that the probability of such an event occurring in our cosmic neighborhood at any given moment appears to be extraordinarily small. Standard model calculations suggest the lifetime of our current vacuum state exceeds 10 to the 100th years, an unimaginably vast timescale, far, far longer than the current 14 billion year age of the universe. We are not in immediate danger. However, the possibility, however remote, remains. Some physicists have expressed concern that future ultra-high energy experiments could, in theory, trigger such a decay. Each new energy frontier explored by particle accelerators probes conditions that haven't existed since the fractions of a second after the Big Bang. It's conceivable that unknown physics at these extreme energies could destabilize our metastable vacuum. The very possibility of vacuum decay reveals just how precarious our existence might be, balanced on the edge between cosmic order and a chaos we cannot even imagine. A transition from a false vacuum to a true vacuum would represent the most complete possible destruction and recreation of reality. It wouldn't just destroy existing matter. It could rewrite the 19 fundamental constants of the standard model of particle physics that determine particle masses, force strengths, and interaction probabilities. In the true vacuum state, these constants could have completely different values. Imagine if the electromagnetic force suddenly became 10 times stronger. Atoms would collapse as electrons were pulled into their nuclei. If it became 100 times weaker, electrons couldn't remain bound to nuclei, and atoms would fly apart. In either case, chemistry as we know it would become impossible. Changes in the strong nuclear force would be equally devastating. If it became too weak, atomic nuclei would disintegrate into individual protons and neutrons. If it became too strong, protons might fuse together uncontrollably, creating exotic forms of dense nuclear matter. The electron's mass, another critical parameter, could change, leading to tiny atoms with alien chemical properties or atoms that couldn't form at all. Even more fundamentally, space and time themselves might have different properties in the true vacuum. The number of spatial dimensions could change from 3 to some other value. Gravity might operate through entirely different mechanisms. The transition process would obliterate all existing structures before the new physics could create replacements. The energy released would vaporize everything into a plasma of elementary particles that would then reform according to the new alien physics. The very logic of physical law could be different. But the perplexing question of our vacuum stability leads us to the single greatest failure in the history of theoretical science. As we've seen, every point in space is alive with the zero-point energy of quantum fluctuations. When physicists try to calculate the total energy density of the vacuum by adding up all these fluctuations, the result they get is absurd. The theoretical prediction for the vacuum's energy density exceeds the value we observe from cosmic expansion by a factor of 1 followed by 120 zeros. This is famously known as the vacuum catastrophe. No other scientific theory has ever been this spectacularly, colossally incorrect. It is a catastrophic disagreement between our two best theories of reality, quantum field theory and general relativity. To put the number 10 to the 120th in perspective, the ratio between the size of a single proton and the size of the entire observable universe is only about 40 orders of magnitude. The vacuum energy discrepancy represents a mismatch on a scale that transcends any other in the known physical world. If the vacuum's energy were truly this high, its gravitational effect would be overwhelming. Space itself would be curved so dramatically that the universe would have collapsed in on itself in the first fractions of a second after the Big Bang. But clearly, it didn't. We are here. So, for some reason we do not yet understand, this colossal energy appears to have almost no gravitational effect. Perhaps some unknown cancellation mechanism is at play, like the one proposed by the theory of supersymmetry, where for every particle contributing positive energy, a superpartner contributes negative energy. Or perhaps general relativity itself needs to be modified on the smallest scales. Resolving the vacuum catastrophe is one of the holy grails of modern physics, and it may require revolutionary advances in our understanding of space, time, gravity, and matter. One of the most speculative but tantalizing ideas to emerge from these puzzles is that our universe is just one of many in a vast, sprawling multiverse. The theory of eternal inflation predicts that while inflation ended in our cosmic neighborhood 14 billion years ago, it continues forever in other distant regions. These inflating regions occasionally spawn new bubble universes, each one beginning with its own Big Bang. This process, called bubble nucleation, is the ultimate expression of quantum uncertainty applied to the very fabric of space-time. Just as virtual particles can tunnel into existence, entire universes might do the same. Each bubble would begin as a microscopic quantum fluctuation, undergoing its own inflationary epoch. The physics inside each bubble would depend on how its unique combination of quantum fields settled into their vacuum states. The fundamental constants that govern reality could be dramatically different from one bubble to the next. String theory, a leading candidate for a theory of quantum gravity, supports this picture with its concept of the landscape. It predicts a staggering number of possible vacuum states, perhaps 10 to the 500th power, each with different physical constants. Most of these bubble universes would be sterile wastelands. In some, the vacuum energy would be so high that space would expand too rapidly for any structures to form. In others, it would be negative, causing the universe to collapse in on itself moments after its birth. Life-supporting universes like ours, with a tiny positive vacuum energy, might be extraordinarily rare across the landscape of the multiverse. This precarious balance we observe, our position near the edge of vacuum stability, might not be an accident. The anthropic principle offers a potential, though controversial, explanation. It suggests that we shouldn't be surprised to find ourselves living in a universe with a stable vacuum and finely tuned physical constants, because only such universes can produce complex, conscious observers capable of asking these questions. In a multiverse filled with countless sterile and short-lived realities, we would necessarily find ourselves inhabiting one of the rare universes that permits both the formation of complex structures and long-term stability. The apparent fine-tuning of our cosmos might not be a sign of design, but simply a selection effect. This leads us to the ultimate question: what is the true nature of nothingness? Our journey through the void reveals a profound paradox, that empty space is not empty, vacuum is not vacant, and nothing might be the most dynamic, energetic, and creative force in the entire cosmos. What we call nothing buzzes with an invisible, violent activity, contains unimaginable reserves of energy, and holds the keys to understanding existence itself. The ultimate fate of everything we know, of consciousness, of complexity, of existence itself, depends entirely on the true nature of this void. It depends on whether our universe occupies the deepest, most stable vacuum state possible, or if it is merely a temporary, fragile stopping point on the way to something completely different. If our vacuum is the true ground state of reality, then the future, while bleak, is predictable. The universe will fade into a quiet, lonely heat death over trillions upon trillions of years, but the fundamental laws of physics will remain constant forever. But if our vacuum is false, then a sudden catastrophic transition could, at any moment, rewrite reality. Yet even this might not be the final end. Perhaps the true vacuum state supports forms of complexity and existence that dwarf anything possible in our current physics. Or perhaps, as some theories suggest, the decay process itself spawns new universes, a kind of cosmic rebirth. The void that seems like the end of everything might actually be the beginning of something entirely new. The exploration of nothingness reveals that the deepest questions about our reality emerge from studying what appears to be absent. In learning about nothing, we discover everything. The next time you gaze up at the night sky or look at the seemingly empty space in a room, remember that you are seeing the most active, energetic, and mysterious phenomenon in the universe. Nothing is everything, and everything emerges from nothing, in an endless, intricate dance of creation and destruction that defines the very fabric of reality.